This video is made possible by our sponsors, Google, Vonage, and 8x8. See the video description for links and more information.
Hi, everyone. And we're now on our next session, and with me is Manik Sachdeva from Vonage, and he's going to talk again about how do you scale group calls and what Vonage had to do during the pandemic around that. So Manik, the floor is yours.
Thank you, Taki. Thank you, Chad. And thank you, Chris. Hi, everyone. I hope you're doing well and staying safe. I want to start off by thanking the Cranky Geek team and you for coming to my talk today on scaling multi-party video calls for client endpoints. I'm Manik Sachdeva, and I'm an engineering manager here at Vonage, leading some of the WebRTC initiatives for the video API. As a major player in the WebRTC space, Vonage Video has seen an unprecedented amount of growth due to COVID-19. As an API platform building SDKs, we've always focused on creating use case agnostic SDKs so developers can add WebRTC easily into their application. With the pandemic, we saw an influx of developers and customers building with several use cases, but had challenges with one in particular, multi-party. And today, I'll walk you through some of those challenges on the client side and how we've helped overcome our customers, and I hope you find them helpful as well. So let's jump into what a typical multi-party call might look like. So I stole this slide off the internet, and now I must admit I've never seen Brady Bunch before, but I found this image quite useful to depict the most typical layout that we see in our customer applications. This is known as grid view or gallery view in the industry, and we use it to chat with friends, colleagues, family, and for any different event that we have. And if I look at this layout on a MacBook Pro 16-inch, 9 people with these widgets translate to about 320 by 180 QNHD, or typically in other devices, we see QVGA. And I am taking device pixel ratio into account here so we can have the proper layout and widget size. So in this typical layout, one of the things that we saw was that our developers were setting applications to receive really high bit rates. So I've kind of added some numbers here. It's not the prettiest slide, but I hope it kind of gets the point across. Initially, with this layout, we typically saw our developers send over 3 megabits per second and receive about 20 megabits per second for a total of 23 megabits per second. Now, before we get into the why of this, let's take a moment to show how I'm calculating these numbers. As you can see before, the formula for calculating bitrate is generally horizontal pixels, vertical pixels, so the resolution, multiplied with the color depth. And we're assuming 8 bits here, but if a normal RGB call, 3 channels, 24 bits, the numbers are much higher. Now, I've actually not set that as a bit. I've set the target bitrate because this is what we've seen traditionally as what's really good for an RTC video call for HD is about 2.5 megabits per second. This is because RTC encoding, we're not always sending full frames. We have delta frames that are being sent majority of the times with keyframes and so on. And so knowing this, we can see that the downlink total from the previous slide that I showed is actually 20 megabits per second. Now that's quite a bit on the receiver side. Now let's go ahead and take the sender side and kind of introduce that. So with the publisher sending about over 3 megabits per second, we see that there's a total consumption of 3.2 megabits per second on the uplink. So now let's go back to our Brady Bunch slide and kind of add these numbers and add a little more information here. So this is actually the receiver side. And the receivers in this case, where we saw our customers struggling was they're receiving HD, even though they were not rendering HD, because we're talking about this layout in specific. This meant that the client endpoint was actually decoding HD streams, downscaling the video before it was being rendered on the screen. Note that the sender was sending simulcast, so it was sending multiple resolutions and frame rates, so they could actually leverage different qualities depending on the adaptiveness on the client. Now, I know we're in a world that's getting closer to 5G and have Cat8 cables on the market with fiber everywhere, but this is challenging for most devices. So how do you improve this? Well, let's take a look at our original slide with bitrate calculation and see what we can do. So I've added VGA and QVGA qualities to kind of, in addition to the HD quality, to show you how variable the bitrate can be depending on the quality. So knowing this information, let's go back to our reference slide with the Brady Bunch and see what we can do. So effectively, one of the first things you can do is improve the optimized resolution. So you only receive what the render size of the widget dimension is with the device pixel ratio in account. So in our case, instead of receiving HD, we'd receive QVGA and therefore effectively dropping the incoming bitrate to 150 kilobits per second per widget on the receiver. And in total, that's 1.2 megabits per second. So that means we've dropped the bitrate to almost 1/20th of the original call, leading to a much better experience on the client and not when you perceive degradation, and actually much less CPU exhausted. So you have your fans, spinning at all times. So we have APIs in the SDK to show this, and you can actually change this adaptively. So if your layout changes to a different format, you can actually bring it up and have the other speakers render, a better quality, HD in that sense, or VGA, depending on the layout. So now that we still, on the receiver side, are receiving 150 kilobits per second, we've set the receiver side improvements, but now let's take a look at the sender side. We're sending 3.2 megabits per second, even though we know the exact layout that's being rendered. So knowing this, the rendering of the Brady Bunch, the publisher or the sender side can actually send much less. It can actually go ahead and even, instead of doing simulcast, you can actually renegotiate to only send one specific quality because you know the end-to-end experience is 150 kilobits per second for everybody involved. Being that aggressive, we can actually bring the publisher down to the same bit rate. So this is kind of like the bit rate calculation that we had, the total uplink and download link that we talked about. And this is kind of what I want to show you as the before and after. So previously, we had 20 megabits per second downlink and 3.2 on the uplink. But then after all these modifications and optimizations that we made, we can actually have a total downlink of 1.2 megabits per second and 150 kilobits second on the upload. Again, note that this is if you own the layout end to end, and this is what our slide would look like in this here. Now, if you modify this layout or have other things involved, you might be sending different qualities, and you will definitely need simulcast in that scenario for the adaptiveness on the receiver side. Now, I'm talking about desktop here, but mobile is even a bigger challenge. We're on the go. And that's why I'd like to take a step forward and talk about other modifications and improvements you can make with mobile and web involved. So we've implemented audio fallback enable with our SFU so that bandwidth estimation algorithms let the client know that there's not enough quality for video. So we recommend audio only. So in that scenario, the SFU, will request the client to, stop receiving video. So you have these, we call black frames that are being here instead. Now, this is not the best video experience, but it's much better than actually losing out on the client entirely. So this is actually a server-side trigger event. But you can actually improve this by using get stats on the client and use total encode time from get stats to understand the CPU usage. And you do that by using total encode time over frames encoded or total encode time over frames decoded and make judgments on the client side for turning the video off proactively on the sender side or even on the receiver side. Now, I know this is, a specific. Yes, go for a second.
It's kind of interesting because what we're saying up until now is that we've got different video layouts and we need to think about what layouts we are using, and based on that start strategizing what we want to send and what we want to receive so that we make better use of our CPUs and bandwidth.
Yeah, and you make a great point, Sahi, and that's why I kind of want to move into the next part of my slide, which is talking about active speaker logic. So in this kind of layouts that we're talking about, and I think we're presenting with this, I have a present with my face, Chad, Sahi, and then a screen. Now in this logic here, I'm the dominant speaker because I'm speaking for my presentation. You can actually see that I'm probably the main window in some scenarios, unless my screen is involved, right? So knowing that, you can actually, there's best ways to kind of do this adaptiveness on the receiver side. And you can actually calculate the loudness of each participant and adjust your layout for that. And to calculate the loudness of these layouts, we actually use several WebRTC APIs for this. So we have the get synchronization sources, get stats, which gives an audio level, and web audio, where we do an FFT transformation. And you kind of have a way of identifying how to calculate the loudness of each receiver that you have. In this chart, I'm showing you a benchmark that we did with CPU resources consumed over time. And we did it in several durations, right? 1 minute, 3 minute, 5, so on, and 12. And as you can see, get synchronization sources, which is in yellow, outperforms web audio in red and get stats calculation, which is blue in the long run. And the key thing to note here, this is only for the sender side. Now, if we look at the receiver side, the same, the same legend applies, and we have get synchronization supporting, performing much better than the other ways of calculating. And a key thing to note is that this is per receiver. So this will actually have a bigger impact as the count of subscribers or receivers increase. So if you have 4 people receiving or 5, that improvement is going to it's going to show a significant improvement in the CPU resources that are being consumed on the client. And this actually, this is something that we do for active speaker detection and audio level. And I can actually take this a step forward and combine screen sharing, and because that's always really important as well. We have screen sharing that we need to show in calls, and when screen sharing is in the front, and I just took a screenshot actually for the static layout of VP8 in the RFC for RTP, and we can actually combine both bitrate level optimizations and active speaker logic, because screen share is now the most dominant and the center figure. Everything else is on the side, and I've added some bit rates here so you can see what those bit rates are. I threw 300 kilobits per second, thinking about a static screen with very good detail. But many times you don't need to actually get up to that. Now, knowing this, what I would like to say is, in the original slide of reference, we had 9 participants, and here we see only 3. The other subscribers are actually off of the screen, and you're only receiving audio from them. You're not actually receiving video at all. This is crucial because if you're not rendering them on the screen, you should never be decoding that at all. And you can actually adjust this based on loudest things. So we've seen this done in Meet, and you can just see in Google Meet, 8x8. A lot of these things employ these technologies as well. I want to summarize a bit more. So coming back to saying, we optimize for bit rates to support a variety of networks. Layout management, that can actually be the biggest driver in improving CPU resources, because it makes you make some good decisions about the qualities that you want to receive and render. Active speaker logic and having frequency around that, so you're not moving things around every second. You have some debouncing built in. Audio level calculations and how that's helpful in Chrome specifically. And we can go beyond that a bit. And some of the next things we're exploring and actually looking into are Opus DTX, which is discontinuous transmission, so you can avoid sending background noise like sounds over the network when not needed. So when the encoder using DTX sends Opus packets every 400 milliseconds, you actually have to you don't need to send as much, and you only send the packet without the payload in that scenario. So when the clients, in other scenarios, when the client mutes, you only send silence packets to the SFU, which are generally dropped and not forwarded to the receiver. And DTX is helpful in scenarios where you don't have clients muting, right? People are talking, you're not pressing the mute at all times, and you want to avoid background noise. Other areas of improvements we're seeing is, using VP9 where possible. And I have some benchmark slides that I'll show you next. And that we've seen H.264, with Android to Android calls, specifically the hardware acceleration, since many Android devices, have Qualcomm chipsets. Now, some of the preliminary data that we have for VP9 is that this is actually an iOS to Chrome that we have a VP8 and VP9 comparison here, setting an encoder complexity of 7 and a total CPU of 600 availability. You can see that the different target bit rates that we have. And you can see that VP9 is a bit of a CPU hog on compared to VP8 on iOS here that we're seeing. But the key thing to note is the next slide here on the receiver side, we actually see VP9 perform a bit better. So I put some video sequences in VGA, QVGA, and HD, and respectively at 30 FPS and showing the CPU benchmarkings here to show that VP9 on the receiver side, so the decoding actually performs much better in scenarios, especially in larger and larger parties. This is for 3 receivers, but you can imagine the impact as the receivers increase. This is just preliminary data. I'm not, I don't have any information on SVC here that I can share today with you, but I hope to share more with you in the near future. Knowing all of this, I want to share, a couple of slides of some successful customers that we've seen build on top of our API, leveraging these improvements to have a much better experience. One of them is Vonage Meetings, which is an internal team that built a tool for video collaboration. Another one is Jam, a lightweight voice and video collaboration for remote teams, leveraging a lot of the API, and Remo for live broadcast use cases that we have. So there's a lot of this that's being built, and I want to keep coming back to it, how client is actually the more important thing to tune, because those are, wide variety of resources that you have to deal with, especially in a pandemic where everybody's running on video and a lot on desktop. Thank you.
Okay. Thank you, Manik.
Thank you to our sponsors. Vonage, creating engaging experiences that move with your customers. See more at vonage.com/communications-APIs. 8x8. Embed full-featured WebRTC meetings in your app with the Jitsi as a service beta. Sign up at 8x8.com/crankygeek. We would like to thank Google for supporting the WebRTC community and this event series. Learn more about WebRTC at webrtc.org.